In this video, we're going to talk about the idea of continuity. Oftentimes, we see functions as pictured here, functions that may gradually change over the independent variable, or in this case, we have a length versus time graph, and our length is gradually increasing as time increases, and we notice there are no breaks, holes, or jumps in this graph. It is continually changing throughout the changing time. Conversely, we've seen graphs that do have holes or breaks, or like this step function here, in that we have a horizontal piece and then we jump up to another value and jump up to another value and jump up to another value, and we have these breaks. These functions are not smooth or continually changing as pictured before. If a function does not have these breaks as pictured in the last slide, we say that that function is continuous at those points because there are no holes or breaks. And in this function, we say that at this point, at t equal to 45 and t equal to 30 and t equal to 15 and t equal to 0, these are all points of discontinuity because there is a break, or there's a jump, or there's a hole. So in order for a function to be continuous at a point, it needs to not have any holes, breaks, or jumps in its graph. And so let's look at this function of h of x is equal to the piecewise of x times sine of 1 over x for all x not equal to 0, and it's equal to 0 if x is equal to 0. And so our question is h continuous at the point x equals 0? In order to answer this question, we need to more properly define what continuity is, more than just holes and breaks. The definition of continuity at a point states that a function f is continuous at a if the limit of f of x as x approaches a is equal to f of a. And if f is not continuous at a, then a is a point of discontinuity. This definition is pretty concise at the surface, but there's more to this definition than what first appears. The key is for the limit of f of x as x approaches a to equal f of a, then both f of a and the limit must exist, and they must be equal. So there's a checklist that we can go through. In order to check for continuity, we first have to ask, is our function defined at the point of concern? So a is the domain of our f. So is it defined on our domain? It could be an interval, could be a point. Second, does the limit exist at that point? Or does the limit exist at every point on the domain? And then third, is the limit equal to the defined function at that given point of concern or along the interval of the domain? Using that definition, we can look at this graph and identify a few points of discontinuity. So first off, at x equal to 1, that is a point of discontinuity because f of 1 is not defined. All right, we don't have a defined point for f of 1. If we continue looking at x equals 2, then we see that once again, this is a point of discontinuity because, yes, the limit does exist. As x approaches 2, we have a limit of 1. And yes, the function is defined. F of 2 is 3, but the limit does not equal the function at that point. So therefore, we have a point of discontinuity. Looking further down at x equals 3, we see that the limit does not exist because the limit from the left and right are not the same. So 3 is also a point of discontinuity. And number 5, we see that the limit does exist. However, the function is undefined at 5 because we're going off to positive infinity. And so since we are undefined at 5, that is also a point of discontinuity. Okay, we could argue that at 4, that is a point of continuity because we are defined there and the limit exists from the left and right, and that limit is equal to the function at that point. So x values of 1, 2, 3, and 5 are all points of discontinuity. At x equals 4, that is a point of continuity. Or we could say our function is continuous at x equal to 4. A couple things to remember about continuous functions. If we have two functions f and g that are continuous at some point a, then the following functions are also continuous at a, and assume that c is a constant and n is an integer greater than 0. So if we have two continuous functions at some point a, then the sum of those two functions is also going to be continuous. Likewise, the difference of those two functions will also be continuous. A constant times one of the functions is continuous. A product of two continuous functions at a point are also continuous at that point. The quotient and raising to a power. All of these are continuous at that point A, as long as the functions themselves are continuous to begin with. This can cross over into polynomial and rational functions, and so a polynomial is continuous for all values of x. Any polynomial is always going to be continuous for all values of x. When we have rational functions, so polynomial divided by another polynomial, it will be continuous as long as our denominator is not 0. So any x values that cause our denominator to be 0 are points of discontinuity. For example, f of x is equal to x divided by the quantity of x squared minus 7x plus 12. The function x is continuous in and of itself. The function x squared minus 7x plus 12 is also continuous in and of itself. However, when we divide these two functions, we get 2 points of discontinuity, because x squared minus 7x plus 12 is equal to 0 when x is equal to 3 and when x is equal to 4. And so those are the 2 points at which we have a 0 in our denominator and we have points of discontinuity, because our limits do not exist. As we approach from the left, we are approaching positive infinity for x equal to 3, and as we approach 3 from the right, we go negative infinity. As we approach 4 from the left, we get negative infinity, and as we approach 4 from the right, we get positive infinity. So since those limits don't exist, those are points of discontinuity. We can then say that the function is continuous everywhere else except 3 and 4. If we have composite functions, meaning functions within functions, and if g is continuous at a and f is continuous at g of a, then the composite function f of g of a is also continuous. From that, we can conclude that if we have that same situation, the limit of f of g of x as x approaches a is simply f of the limit of g of x as x approaches a. And we can also conclude that if our function g has a limit that exists at a and it's equal to some value L, and we know f is continuous at L, then the limit of the composite function f of g of x is equal to f of the limit of g of x as x approaches a. This brings us to the idea of endpoints. And say we have this functional segment here where we have a closed circle on the left and an open circle on the right. Well, we see that there's no holes or breaks in between those points a and b. So we say the function is continuous on the interval of a to b, where we include a but don't include b because we have an open circle there. So we know we're continuous at a, but we know that we're not continuous at b. This function would be the flip of that, in that we're continuous at b, but we're not continuous at a. So we say that our function is continuous on the interval of the open a to a closed b. The formal definition of this states that a function f is continuous from the left, or left continuous, at a if the limit of f of x as x approaches a from the left is equal to f of a, and f is continuous from the right, or right continuous, at a if the limit as x approaches a from the right of f of x is equal to f of a. And so if we combine all those definitions of the right and left, we say that a function is continuous on an interval if it is continuous for all points on that interval. And if the interval contains its endpoints, continuity on the interval means continuous from right or left at the endpoints. So if we say that a function is continuous on the interval from a to b and we're including it, then it is continuous from the right and from the left at both a and b. So if we look at this example pictured here in figure 2.47, we see that this function is continuous on the interval of negative infinity to 0, including 0 because we're continuous at that endpoint, and it's continuous on the open interval from 0 to positive infinity. It is an open interval because of the open circle here at 0, and we say that this is discontinuous, or there is a point of discontinuity at 0. We can also describe the point at 0 to be left continuous because the point goes with the left part of the function. If these were switched and this were an open circle and this were a solid circle, then we would say it's right continuous. Now let's turn our attention to functions with roots, and let's assume that we have some integers m and n that are positive with no common factors. And if m is an odd integer, then the function f of x raised to the power of n divided by m, it's continuous at all points at which f is continuous and f of a is greater than 0. So what is this saying? This is saying when we have roots, if it's an odd root, it's continuous for all points in a possible domain. However, if we have an even root, so like a square root, fourth root, sixth root, eighth root, and so on, then it's only continuous if we have a positive function inside the root. For example, say we have a function of 3x minus 4, and we're raising that to the 1/5. Well, that's going to be continuous for all values of a. But if we had 3x minus 4 and we raise it to the 1/4, then that's only going to be continuous when 3x minus 4 is greater than 0. Looking at this example of a semicircle, g of x is equal to the square root of the quantity 9 minus x squared. We see that this function is continuous on the closed interval -3 to 3. That is where we have a positive value inside of our root. And since this is an even root, we have to pay attention to positive and negative inside the root. And we can also say that at these points, we are right continuous at x equals -3 because our continuity continues to the right of -3. And we say we're left continuous at x equals 3 because our continuity continues to the left. Theorem 2.14 tells us that if we have a continuous function f and it has an inverse on an interval, then its inverse is also continuous on that interval containing the points f of x where x is in the interval I. Now using that theorem, we can, and some other reasoning, we can jump to theorem 2.15 and we see all of these functions that are continuous on their domains. Now one thing to point out here, this is continuous on their domain, so all points of their domains. That does not mean, this does not mean that it's continuous on all real numbers. Okay, that is not true. For something like sine, that is true. Sine of x, its domain is all real numbers, and it's continuous on its domain, so it's continuous for all values of x. However, something like secant is not continuous on all real numbers for x, but it's continuous on all of its points in its domain. We know that y equals secant x has vertical asymptotes at pi over 2 and 3 pi over 2 and every successive pi over 2 after that. And so those points aren't part of its domain. However, the points that are part of its domain are continuous. The function is continuous at all of those points. This list also consists of some other functions such as inverse trig functions and some exponential and logarithmic functions that are continuous for all points on their domain. Let's finish by talking about the intermediate volume theorem. In this picture we have a function on the left, y equals f of x, and we see that this function is defined on the interval a to b, and there's at least one number c that's in between a and b that gives us a value of L that's in between f of a and f of b. All right, and so we see that point right there, and it might not seem all that significant, but it'll get more significant as we talk about it. If we look at this second function on the right, once again, if we have some value L that's in between f of a and f of b, now notice f of a is greater than f of b on this one, where it was the opposite on the other side, and that doesn't matter. We just have some point, some value L between f of a and f of b, and there has to be at least one value c that corresponds with that y value, and c has to be between a and b on the x. One thing to notice about both of these functions are continuous on the interval a to b. Looking at a function that's not continuous on a to b, because we have this break, this jump, we see that some value L that's in between f of a and f of b does not have a c value at which our function is equal to L at that c, and that is because our function is not continuous. And so this leads us to the intermediate value theorem that states, suppose we have a function f that's continuous on an interval from a to b, and L is a number strictly between f of a and f of b. That's the only provision on L. Then there exists at least one number c in the interval a to b that satisfies f of c is equal to L. Now, one thing to notice here, I didn't say it when I was reading it, but this is an open interval a to b, not including a and b, and this is a closed interval that does include both a and b.